In this video, we're going to look at Newton's second law for rotation for a more general case where the moment of inertia may not be fixed. It is possible for an object to have a constant mass but not have a constant moment of inertia. This can occur because the axis is being changed, or this can occur because the object is changing its shape and thereby the distribution of mass. So in the same way that when mass was changed, we needed to use the fact that the sum of the external forces was equal to delta P over delta T, or more precisely at the more advanced level, the limit as that occurs, as delta T goes to 0. Because we did this, we need the same sort of thing in this chapter for rotation, but it won't be the sum of the forces. It'll be the sum of the external torques. And it's equal to the change not in the linear momentum, but the angular momentum divided by the change in time. So this extremely important equation explains an awful lot of things in the world of physics. For one, it tells us when delta L will change and what the cause of that is. It says that the change in angular momentum is caused by torques. So it says that torques is the cause of change in angular momentum, just as force was the cause of change in linear momentum. And we can sit here now and define something that looks a lot like the impulse that we had back in the chapter on linear momentum. We can bring the delta T over next to the torque and say that the sum of the external torques times delta T gives us the change in the angular momentum. So this is kind of like a rotational equivalent of impulse. Doesn't actually have a name that I know, but it is the equivalent of what impulse was. And we found that, well, this is true if this doesn't change much. In general, this torque could be changing, and if it is changing, what this means is it's the area under a torque time graph. So the change in angular momentum in general will not be a rectangle, base times height. It'll be some more complicated shape, and what you're really looking for is the area under the curve. So delta L is area under the torque time graph. So if you have a graph like this and you wanted to find the change in angular momentum, let's say out to here, then you're looking for this there. That's delta L. It's delta L from t equals 0 to t equals 4. Now, let's take a look at one of those problems and using both of these two laws. The first one says the angular momentum of a flywheel having a rotational inertia of 0.2 kilogram meter square about its central axis decreases from 3 to 0.4 kilogram meters squared per second in 2 seconds. What is the magnitude of the average torque? Well, this is an example of applying the second law. The sum of the torques is equal to delta L over delta T, which is L final minus L initial over delta T. The sum of the external torques is equal to, the final it says is 0.4 kilogram meters squared per second. The initial was 3 kilogram meters squared per second, and we divided by 2 seconds. So the sum of the external torque in this case, and grab my calculator and I get 1.3, at least if I'm looking for the magnitude, which is the absolute value, 1.3, and that's a Newton meter. So that's the torque that you would have to supply to be able to create this change in angular momentum. Now, you can also ask a different question. This one says, how much work is done on the wheel? So how would I calculate that? Well, I remind you of a few things. We know that the net work is delta K. This is known as the work energy theorem. Now, back in linear land, we as K was 1/2 mv squared, but you could also have written it by multiplying top and bottom by m as p squared over 2m. So now we have K, replacing the p with L squared, and the m with I is over 2I. And this is very useful on this problem because I know L and I know I. I was given L and I was given I. So I can find the change in kinetic energy and thereby with the work energy theorem find the amount of work done on the wheel. So W net is equal to 1 over 2I times L final squared minus L initial squared. W net is 1 over 2, and I need the moment of inertia. Let's go up and see what it says that was. It says the moment of inertia was 0.2 kilogram meter squared. Okay. 0.2 kilogram meter squared. And then we had, what was it, 0.4, I think? Yep, 0.4 kilogram. 0.4 kilogram meters squared per second minus 3 kilogram meters squared per second, and each one of those needs to be squared. And let's see what that gives us with our calculator. 0.4 squared is 0.16 minus 3 squared is minus 9, and then I divide that by 2 and divide it by 0.2, and I get minus 22.1 joules. So you can see in this problem that I'm still using stuff out of the chapter on work and energy. I still have to know the work energy theorem. I'm just using our new kinetic energy for when you have an object that just goes in pure rotation, L squared over 2I. And I prefer that to 1/2 I omega squared because I wasn't given omega, I was given L. Here's another problem. We have one of these things where I said you could find the area under the curve. It says the figure below gives the torque that acts on an initially stationary disk that can rotate about its center like a merry-go-round. The vertical axis is marked in increments of 0.25 Newton meters. What's the angular momentum of the disk after 5 seconds? Alright, so we're looking for the area under the curve, and I can find that by breaking this into 3 parts. This part, and this. So I got this, and all of that. Good. Let's go ahead and do the computations. It says 0.25 Newton meters, so this is 0.5. This is 1. This is 1.5, and this is 2. So delta L is L final minus L initial, but L initial was 0 because it said it was stationary. This is the area under torque T graph. So delta L has to do first with this little green rectangle, which is 1/2 a Newton meter times, it appears to be 2 seconds. Then I have to add this little triangle, which has a width of 2 and it has a height of 0.5. So 1/2 Newton meters times a height of 2 times the fact it's a triangle, it's 1/2 base times height. That 2 cancels that 2. Plus, I had a 1.5 Newton meter height of a rectangle times a total of 5 seconds. So delta L is, this is 1, this is 0.5, this is 7.5. 7.5 and 0.5 makes 8, plus 1 makes 9. So this is 9 joule seconds. That's the change of angular momentum for this particular problem. Now, angular momentum, that is the area under this curve, can be equal to 0. That is, delta L can equal 0, and we say angular momentum is conserved. It can do this in one of two ways. The sum of the torques is 0. This is called an isolated system. Or delta T equals 0. In explosions and collisions. So if either one of these cases occurs, such as you're on a spinning wheel and you have a basically friction-free axle, then there won't be any torques that can be applied to you. And your L before and after has to be the same. On the other hand, you can have explosions and collisions because even if there is a torque, it can't have much time to interact. It won't be able to change the angular momentum much, if at all. All right, we'll see you on another video.